Okay, this is a video about Hess's law. This is 6.3 in our textbook. So, just to review with you a little bit, heat is, there should be an is here. Heat's always transferred, either from system to surroundings or surroundings to systems. Um, you also just talking about enthalpy. You can't directly measure H, but we can get delta H values. And at constant pressure, we can calculate delta H by calculating Q. So Q and delta H are equal for most everything we do. And then delta H, if it's an endothermic process, it's positive. If it's exothermic, it's a negative. Um, and just to kind of reiterate that enthalpy is a state function. So that's one where it doesn't matter really what path it takes. It just matters what the beginning and the ending enthalpies are. And because of that, we can use Hess's law. Hess's law is something that we do if there's a certain type of reaction that we can't really do calorimetry for, so we can't determine the Q are the way that we normally do. An example of this would be graphite turning into diamond. It happens at such a slow rate that it's not conducive to us trying to figure out through using calorimetry. Just to review with you before we start getting into Hess's law, these are the enthalpy diagrams, sometimes called potential energy diagrams. So you know that if something's endothermic, you're going to end with products that have more energy, potential energy stored in them than they had to start with. And then if it's exo, your products have less. So that's why the exos are negative and the endothermic values are positive. So this is just me. I'm going to explain Hess's law with this. So this is just an example. Let's say that I didn't know the delta H of this particular reaction. We'll call this reaction the target reaction. And what we do know, though, are the delta H values for these two, what I call sub-reactions or data. So these are always going to be given to you when you do one of these problems. So, for some reason, I may be unable to do this reaction and get the good data from my calorimeter, but I do know for sure that if I, react nitrogen and oxygen and I get nitrogen monoxide, it's 180 kilojoules of energy absorbed. And then if I take that nitrogen monoxide, react it further with oxygen, form nitrogen dioxide, then it's an exothermic. So what we can do is similar to redox, where we would cancel out like terms and we would get our electrons equal on both sides of the arrow. We can do the same thing with substances in reaction. So I can cross out the nitrogen monoxide because it's made and then it's used up right away. And then leftover, I can write add these together essentially. And this gives me, if I did it correctly, I should always get the same reaction as what my target reaction is. And then I can add my delta H's together. And for me, I end up getting positive 68. So that then tells me that that reaction without doing calorimetry is going to absorb 68 kilojoules. So here's another way of looking at it. So this is showing you in blue are the two sub-reactions or steps. And you can see one is endo, one is exo. Overall, if you look at just the beginning reactants and the ending reactants on the right side, it's going to be equal to 68 kilojoules, which would be an endothermic process. So there's rules that you need to use when you do these calculations. One of them is if you reverse a reaction, the delta H sign reverses. So if I read this reaction, this first one, it's showing me that xenon reacts with fluorine and it forms xenon tetrafluoride. And in that process, it is going to give off 251 kilojoules. But let's say, and you'll understand once we do the problems, that I want to reverse the reaction. So I want this now to be the reactant and these to be the products. That's what I have right here. When I reverse it, I reverse the sign. So my delta H is positive now. I don't need to put the sign there, but it's not negative anymore. So that's one of the rules. If you reverse the reaction, the sign of the delta H is reversed. Another rule is if you have to multiply the reaction by a given number, you also multiply the delta H by that. So let's say I want to have 4 fluorines instead of 2. So I would multiply this whole reaction times 2, but I would also multiply the delta H times 2. And those two, whatever they are, rules that I just showed you are what we're going to use when we do Hess's law. So we're going to do 2 problems. I would recommend maybe following along if you haven't done one. You could follow, or you could pause it and try to do it and then check, after you've done it, unpause the video. So this is a question about a beetle. The bombardier beetle explosively discharges this compound, and the reaction that's involved is given here. So this whole reaction is what I would call the target reaction, and for some reason we can't directly measure the enthalpy change with a calorimeter. So what I recommend doing is, and I'm going to switch to this slide so I have more room. If you're at all struggling, I would recommend color coding. So this compound here, I try to find it in a reaction below. So these are my data reactions, and I find it's right there. So for me, I know then that it's on the right side, so I don't need to reverse the reaction, and I don't need to multiply it because it's equal to 1 mole. So everything is good for this one, and my delta H stays the same. The next thing that I'm going to try to match up is the peroxide. And I see the peroxide in this data reaction. So you can see that in the data, it's on the product side, and in the real reaction, the target, it's on the reactant side. So this whole reaction needs to be reversed. So I'm going to write it as H2O2 becomes H2 plus O2, and then my delta H is going to be positive 191.2. Next thing, I would try to pair up the liquid water. So there's a few waters here. You have to really be careful of the state of matter. So I'm going to pair that with this one. And the liquid water is on the correct side, so I don't need to reverse, but I do need 2 moles of it. So I'm going to multiply this whole reaction times 2. So I would have 2 water. Now I'm going to keep track of the state of matter because you'll see that it matters. So my delta H value is now going to be multiplied by 2, which would be negative 572 kilojoule. So it looks like everything's going to cancel, but it won't. So you cannot cancel the gas and the liquid of the two when you're trying to add these data reactions together. So the next thing that I do is I look at, okay, I know I want the water liquid, but I don't want this. I need that to cancel. So because of that, I'm going to look at this reaction now. And normally we want it to be on the same side, but this one we're trying to cancel. So we are going to reverse it and multiply it by 2. So, just wait, don't reverse it. Sorry. Just multiply by 2. I want, sorry. I want to make sure that the water gas is on the opposite side as the water that I want to cancel. So all we need to do is multiply by 2. So when I do that, my delta H is negative 483.6. And then that reaction times 2 would be this. Okay. Now you're ready to cancel and add these reactions together. And I will show you. So we have 2 moles of hydrogen here and 2 moles here. So the hydrogen will cancel, which is good because it's not in our overall target reaction. And then the water gas will cancel. And the oxygen will. So what I'm left with is going to come down now. So I've got these on the reactant side, and I have these on the product side. And I would write that. And then I can sum all of my delta H's together. So I know that this reaction has an overall enthalpy change of negative 687 kilojoules. So, and then another check that we did it right is the target reaction right here is the same as what I got. So they're kind of fun. Anyways, I would try another one. So this one, I would try to do it and then check your answer with me. So I would pause this and then try the problem. So this one, I'm going to just highlight quickly what I'm pairing up. And so just you can see that the first reaction is fine the way it is. Second one needs to be reversed. Third one needs to be multiplied by 3. And then the fourth one needs to be multiplied by 3. And we will see how that works. So, first reaction, delta H just stays what it was. Second one, we're going to reverse it. So now these are my reactants. The water there, let me just grab that. This is gas. So the state of matter matters if there's more than one of the same substance with different states of matter. So that one we reversed it. So the delta H is going to be positive 1273. Oh, I think I wrote, just wait, I'm off by one. That one second. So the first one was fine. We kept it the same. Oh, second one is reverse, so it'll be positive 2035. Third reaction is multiplied by 3. And our delta H is also multiplied by 3. So we end up with negative 858. And then the last one, just wait. We're also going to multiply by 3. And for that one, we'll get 132. So the last one would be oops, sorry, 3 waters, liquid, go to 3 vapor. And I took this times 3. So this times 3. This one I reversed, and that one I kept. So when I add, I should get 36. And then when I try to cancel, let's hope it works. I'm going to cancel my oxygen. So 3 halves and 3 halves are 6 halves, which is the same as 3. I am going to cancel the B2O3. I am going to cancel the liquid water. And then, I didn't put the state of matter. That's the gas. So the gaseous water will also cancel. And now I'm left with 2 borons, 3 hydrogens, and 1 diborane is what it's called. So 2B plus 3 hydrogens makes diborane. And that does match the target reaction, so I can be confident that I'm correct. There are more of these in the textbook if you want to practice, and more in the web assign.